All right, so second to last lecture, problem set 11 due tomorrow. You know that we're dropping your lowest problem set score. So if you've done swimmingly on problem sets 1 through 10, please don't not do this. Let me put it this way. You should do this problem set because this is the kind of stuff that we're going to love to be testing you on. Okay? Don't just blow it off and say, "Oh, I'm doing great." Do it just for your own sake. And if you're super cool and you think you've done great on the homework, don't even turn it in. But still, just do it. Do it. You gotta do it. All right. So then there's going to be a talk tonight. Review for the final will be May 5th, 11 to 1 p.m. It'll be in this class until further notice. We're going to just sort of make sure that we can get this class, but I think it's not going to be a problem. The final, as you know, May 12th, 3-hour final, 2-hour and 50-minute actually. That's in Echeverry, and that's starting at 8 a.m. Sections, the last sections, will be this Friday and the following Monday, May 2nd. These are not counted on your participation grade, so you do not have to go. But like problem set number 11, you should go to that. We can't ask you to go to that, though, but we can ask you to do problem set 11. My office hours is normal today. Yeah, 4:30. Any questions on logistics? Everyone's got it? Okay. Oh, yeah. So 2 lectures that may be of interest. The astronomy colloquium is Lars Hörnquist from Harvard. He's very well known for doing large-scale simulations of galaxies and the universe. He's going to be talking about the origin of spiral structure in spiral galaxies, so that may be of interest to some of you. And that's at 4 p.m. on Thursday. And then at 4 p.m. in 2 LeConte, instead of 1 LeConte, where the colloquium is, there's a former professor from Berkeley, whose first name is Nima and the last name is hard to pronounce. And he's basically a string theorist plus sort of a phenomenologist. So he's sort of hardcore physics, but he's going to be giving a sort of popular lecture for physics undergrads. And I think it's called The End of Space-Time. So I don't actually know what that means. But it may be of interest for those that are thinking about the beginning of space-time in the context of the Big Bang. Because maybe it's like what happens at the end. I don't know. We'll find out. So I encourage you to attend those if you can. So last time, we sort of wound up simplifying the Friedmann equation to be h squared, r squared times the quantity 1 minus omega. And now omega, if it's not subscripted, you should be thinking of omega total. Omega total is omega relative plus omega lambda plus omega matter. And we can also subscript this with a 0. So this is the values today. Omega relative today. Relativistic today, omega lambda today, and omega matter today. And the summation of these 3 quantities is almost exactly 1. And because that value is almost exactly 1, it means that the right-hand side is basically 0. So what I've been telling you about a flat universe is approximately correct observationally and may be exact. That's something that people are trying to figure out. Which of these 3 terms dominates today? The Friedmann equation? That one. What's the second most dominant? Matter. And the last one, relativistic particles don't contribute much at all today. All right? So as you know, when you're trying to figure out the dynamics of the universe, how R is changing as a function of time, or how R is changing as a function of redshift, you have to know how these different quantities wind up scaling. And one way we can understand that is in the context of the Hubble constant as a function of redshift, and be thinking about the Hubble constant because it is itself defined to be r dot divided by r as the rate of expansion of the universe at that redshift, okay, as divided by the scale factor. So h of z we found last time is whatever the Hubble constant is as measured today times 1 plus z. Times this massive quantity in brackets, omega matter 0, 1 plus z, plus omega relativistic today, 1 plus z squared, I think, yep. Omega lambda today divided by 1 plus z squared, plus 1 minus omega 0. Right, this is found by setting this equation on the right-hand side equal to h naught times h naught squared times r naught squared 1 minus omega naught, right? because k is going to be a constant for all time. So we can just do this as a function of redshift relative to what we observe today. So everything we observe today, in particular the Hubble constant, winds up setting the scale and the age of the universe directly. In trying to figure out what this whole mess is, remember what we showed is that the luminosity distance is 1 plus z times this thing called the proper distance. And the luminosity distance, remember, was defined such that our normal sense of the 1 over r squared law holds, such that flux is equal to luminosity 4 pi dl squared by definition. And what we showed, because of two contributing factors, not competing, the reason why this isn't the proper distance, it's because of time dilation, right? So the rate of the arrival of photons is changing as a function of redshift linearly, and the loss of energy of those photons. We showed, lastly, that the proper distance was just this scripty L that we talked about when we did GR and we did special relativity, and that's just the integral of minus ds squared, square root of minus ds squared. And through a little bit of hocus pocus, we found that that was just c times the integral from 0 to the redshift that you're looking at, dz divided by h of z, which means that if we can constrain the luminosity distance by measurements, say, of supernovae, then what we're effectively doing is constraining the integral of h of z. So if we do this as a function of redshift, we're constraining this integral as a function of redshift, which is our way of making constraints on all of these different quantities of interest here. And remember, if we're looking sort of nearby, we can throw out the relativistic term for the Hubble constant. And we can just pay attention to the matter and omega lambda and 1 minus omega 0. And we can assume that this is about 1, so we can throw that out. So we get sort of in the low z limit, less than redshift of 1, a nice functional form, a smaller functional form for what the Hubble constant is as a function of redshift, or likewise what the luminosity distance is going to be. Remember, I showed you that you can crank up and down omega matter and omega lambda independent of each other, but if you fix this quantity to be exactly 1, then if you crank one up, you've got to crank the other down. And the fundamental point that I wanted you to take away from the last lecture is that in a universe with a fixed amount of omega matter, like 0.3 or 0.27, something that you might be actually able to measure where you're not appealing to cosmological observations, but instead observations of, say, clusters of galaxies, in that universe, well, of course, omega total would be less than 1, right? So it changes our understanding of the topology of the universe. But you have a certain fixed brightness as observed of a supernova at a fixed redshift. If I now turn on the cosmological constant, those supernovae become brighter or fainter? Fainter. That's right. So in a universe that has a cosmological constant, supernovae are fainter than they ought to be for a fixed redshift. And that's one of the fundamental things that I wanted you to take away from the last lecture. Are there any other questions? You guys completely got it? All right. So in addition to our concept of luminosity and flux and essentially the 1 over r squared law, there's something else that we might intuit when we're trying to come up with cosmic rulers, cosmic ways of making measurements of the Hubble constant as a function of redshift. And that's some sort of concept of an angular distance. In the concept of an angular distance, you might, instead of calling it dl, you might call it dA. And this is just going to be defined to be some sort of size scale of the source that you're looking at divided by theta, the angular extent of that source. So L is some size, in, say, megaparsecs of some source. Theta is the angular extent. And this, of course, jives with your understanding of how we do the geometry of this problem, right? So And obviously, this is for small angles. So here's some very distant source whose size we can know, right? Essentially, it's a big ruler in space. And we look at the angular size of that, and we say, oh, that's 0.247 radians. And I know it's, whatever number of megaparsecs. Therefore, the distance from us is this. We define the angular diameter distance like this. Now, how do we think about this in the context of the metric? So remember the Friedman, Walker, Robertson, blah, blah, Lemaitre metric. What do we say? F, R, W, etc. So think of this now as two events. We have photons leaving from opposite sides of a source. So now we have photon here and photon here, and they're heading towards our eye. And one day we're going to wind up detecting those photons simultaneously, and we go, there's a big ruler in space. And it's got this size because I have a photon that's arrived from one end, and I have a photon that's arrived from the other end. We'll say that those two photons, because we're going to observe them at a fixed time, and these things are going to take the same radial path with respect to each other. Right? So if I now set my origin right here, I can now do the metric in spherical coordinates, and I can say that r varp, is equal to 0, and there's going to be some distance from here to here. But the point is that if I'm observing them at the same time, and we're talking about photons propagating essentially in vacuum, then we would certainly say that the time that these two photons left relative to each other is going to be 0. Likewise, if I now associate this with some distance, r varp, it's pretty clear also that if these photons are taking the same path, we're going to set this equal to 0. And likewise, if I'm thinking about this now in the context of an angle theta, not so much in sweeping around in some 2 pi sense, we'll just set d phi equal to 0. If you go back to the metric, I won't rewrite it, you wind up getting that the first term that we usually wind up playing with when we talk about the radial term, dr varp squared divided by 1 minus k r varp squared, that goes away because of this. The time term goes away, that second term goes away, and the last one winds up remaining, and we wind up having minus r squared of t, r varp squared, d theta squared. Now in this context, the proper length, which I'm calling this little l, is actually just the same as the big L that we've been talking about in the past. So this is just the integral of square root of minus ds squared. And this is from 0 to pi, taking the square root of r of t d varp d theta. Right, so now I'm going to sweep in theta from basically 0 to pi. 0 to theta, excuse me. Okay, so this is a pretty easy integral to do. Just r of t, r varp theta. All right, so how do we think of theta in this context now? This is just L, just putting the R and R varp on the other side. Theta is now R of t times R varp, and this, of course, is L dA by definition. Okay, so dA is R of t, R varp, and now we get to play a little bit of trickery. r of t divided by r0 times r0 r var p. What's this out in front? What's that? Nope. No, what's the scale factor in the past relative to the scale factor today? Redshift. Yep, 1 over 1 plus z. So this is r0 r var p divided by 1 plus z. And what is this up on the top? Yeah, it's the physical distance between us and that source today. So what have we been calling that? Proper. Proper distance. Wow. You guys got it today. So dA is equal to d proper 1 plus z divided by 1 plus z. And if we put in what I already erased, what dl is relative to 1 plus z, you find that dA is equal to the luminosity distance divided by 1 plus z squared. Okay, so all of a sudden your concept of a 1 over r squared law sort of jiving with the idea that sources that are farther away get smaller starts to break down. There's now a fundamental difference between dA and dl. So the way in which you make measurements of sources emitting light to you and the rate at which it comes at you and the sort of energy that's coming at you is fundamentally different than the way in which you make measurements of angular size on the sky. And at first glance, it's not a really big deal because you say, there's only a sort of 1 plus z factor, right? And obviously your concept of z being earlier in time and also being farther away is not such a bad idea in the context of a luminosity distance. At higher redshift, sources are just fainter, right? As I go farther and farther away, the sources get fainter. As I go to higher and higher redshift, the sources go fainter. Likewise, you'd think that if I have this standard ruler, in this case a piece of chalk, and I start moving farther and farther away from you, that it would get smaller and smaller as I go farther and farther away in angular extent. Now, if I'm not moving in distance, some sort of proper distance sense, but I'm now moving farther away from you as in I'm moving at higher redshift, what actually happens is I go farther away at higher and higher redshift, all of a sudden this chalk starts to get larger and larger and larger. Here is for different cosmologies, and as you can see, of course, because dA depends on d proper depends on Hubble constant depends on the values of these fundamental quantities, we wind up having different values of the apparent angular size as a function of redshift. And what's very remarkable, it's something that you'll show on your problem set, is that if you take the equations that we have for dA, and you couch it in terms of the parameters that we observe today, omega matter and omega lambda in particular, you wind up seeing that there is a minimum to the size that a source of fixed length would appear to be on the sky. That is, if I take this piece of chalk and I go farther and farther away, it's going to get smaller and smaller and smaller. As I get to sort of a redshift around 1.5, or I think 1.7 in the preferred cosmology, all of a sudden it starts getting bigger and bigger and bigger, even though it's getting fainter and fainter and fainter. So this is super weird, and it's okay to be freaked out by this. I can tell that you're all super freaked out. So dA gets larger with redshift. Yes? I can try. Give me a sec. It's larger with redshift until z of about 1.7. Then it gets smaller. it's as if the source is closer to us in some sort of angular distance sense as I go beyond redshift of 1.7. In fact, at redshift of 5, we have the same angular extent of a source of a fixed size as redshift 0.5. And yet, in luminosity distance, we've changed by something of order a factor of 10. So the thing is 100 times fainter than it would be if it was a redshift of 0.5. Okay, so what is it that you wanted me to try to do?
Explain this curve from A equals TL over.
All right, so let me draw for you. I'll just erase this. Let me draw for you, just schematically at least, dA and dL as a function of redshift. So dL is doing something like this, log of some distance measure. It's just going up and up and up as I get to higher and higher redshift. And what happens at nearby distances, because of course your idea of the 1/r squared law driving with this angular distance thing has to work at small distances. It winds up departing like this, and around 1.7 this thing turns over. And actually, as you get to as z goes to infinity, dA goes to 0. Which means a source of, size, the size of an angstrom, would actually appear to be covering the entire sky, if you could see something at redshift of infinity. So this has some functional form. Remember, this goes like 1 plus z d proper, and this goes like d proper divided by 1 plus z. So they're only different by 1 plus z squared, but it matters a lot. Yes?
So when it gets bigger, so like, is it still the same total luminosity for that surface area? So essentially, like, per surface area is getting much, much fainter?
Yeah.
Okay, so like, it's going to get to like a limit of it's impossible for us to see.
Yeah. And in fact, what we'll talk about in the context of the cosmic background radiation is that we basically can't see any electromagnetic activity beyond redshift of 1100 anyway. But we're really interested in figuring out not so much the flux of the CMB, because that's things that we could just measure by getting the temperature. It's figuring out sort of typical size scales of the CMB. But you're right. If you were able to probe all the way farther and farther back beyond the CMB, it would get fainter and fainter, even though it's getting bigger and bigger on the sky. Does that help? Slightly help. Remember, d proper is just going to be some integral of 1 over the Hubble constant, right? That's it. And so if we know those parameters, we got that value. Yeah. I've been working on a source recently that's at a redshift of z of 0.3534. And in today's cosmology, the luminosity distance is about 1,800 megaparsecs. And the angular diameter distance is about 1,000 megaparsecs. It's like 995. So even at a small redshift of 0.3534, there's almost a factor of 2 difference in what the angular diameter distance is and what the luminosity distance is. Okay. Good, it's confusing. Well, this is interesting, right? Because it means that if I have a way of making measurements of some sort of intrinsic sense of the size scale of something in this direction or this direction, and I assume that they're the same, then I have effectively what you might call a standard ruler. Just like in the context of luminosity, there is no such thing as a standard candle. There is no such thing as an absolutely standard ruler. There's usually some messy physics. So you generally have to make a standardizable ruler. So we'll put that in quotes. there's a couple of standard rulers in cosmology that we make use of. There's the Sinayev-Seldovich effect. I'll talk about that towards the end of class today. That's sometimes called the SZ effect. There's cosmic background radiation. Or the CMB. And there's sort of a new thing called baryon oscillations. These two are related to each other. It has to do with perturbations in the early universe that wind up being manifest as something we can observe. In this case, you observe this in the power spectrum of the cosmic background radiation. In the context of baryon oscillations, you observe this in the power spectrum of the distribution of galaxies with respect to each other at redshifts less than 1100 or so. I think we'll do baryon oscillations. This is sometimes called BAO. I think we'll do baryon oscillations on Thursday. As sort of the last thing that we talk about in the context of observational cosmology, and then we get sort of what happens in the very, very early universe. We'll talk about CMB now, and then I think we'll try to end with the Sinayev-Seldovich effect. So all this stuff, even though it's interesting physics in its own right, we'll wind up seeing we're going to do in the context of observations that are going to give us some of these parameters that we're interested in. All right, so I'm going to put the board down in a second, so the screen. So let me just start off with a couple of statements about the CMB. The temperature of the cosmic background radiation is 2.725, as your book calls it, and that's today. So this is cold, and this describes essentially the average energy of photons that are coming from this, what's now called the surface of last scattering. We'll see that before. And to give some context, because the CMB comes from a special moment in the history of the universe when the universe got cold enough that we could have neutral atoms for the first time, it's appropriate to think about the temperature of the universe in a radiation-dominated sense. Remember, I'm just rewriting what we found before. The temperature of the universe is going to decrease as time goes on, and the scale factor of the universe is also going to get larger as time goes on. We showed this before in a radiation-dominated universe. Let me come back to that in a second. That's just to give some context. What's actually happening at this special moment when the CMB photons are being created, released, and then propagate out to our detectors, essentially not interacting with matter for that entire time? This is obviously just a schematic, but what you have at high redshift, at the top, where the temperature is very hot, you have a bath of photons. You might think of these as the yellow background. And those bath of photons have individually enough energy such that if they encountered a neutral atom of hydrogen or even helium, you would wind up ionizing, right? So remember, the ionization potential of hydrogen is 13.6 eV. That corresponds to something like 150,000 degrees Kelvin. So if you have 150,000 degree Kelvin gas and it's got lots of photons in it, the average photon has enough energy to ionize any hydrogen atom it meets. So think of everything at redshift beyond some magical redshift called the recombination redshift as more or less a plasma of ionized particles. In this case, because we haven't had any stars that have turned on, all we're talking about is the stuff that was made in the very early universe, things called, in a process called Big Bang nucleosynthesis. We basically just have helium and hydrogen. And the helium nuclei, 2 protons, 2 neutrons, are freely floating around, and they don't have any bound electrons to them. And likewise, there's no bound electrons to individual proton atoms, so there is no bound hydrogen. Right? Of course, momentarily, you could have a density which is high enough, and you could interact right? With say a proton and electron, you could temporarily have some, neutral atom, but very quickly a photon comes along and says, "Oh no, you don't." Okay, so it's just a big plasma of ionized stuff and very hot photons. Now the universe is expanding and it's cooling, so the densities are going down, right? But more importantly, the temperature of the average photon, the average wavelength of the photon, is not now short enough to be able to easily ionize any neutral particle. So eventually the universe gets cold enough that all of a sudden there's a proton and electron, and they can wind up recombining, or just combining, because it turns out they were never actually combined. So recombination is a bit of a misnomer, but it's called recombination because they wind up combining together. Okay, and then you can have neutral atoms and neutral hydrogen atoms, neutral helium atoms. So from this moment to this moment, what happens to the photons? There's some photon which has an energy which is just the right amount to sort of ionize a hydrogen atom. And all of a sudden the universe expands by epsilon more. And now I have basically enough energy to ionize a hydrogen atom. But the density has gone down, so I may not even interact with a hydrogen atom. Right? This is all some sort of probabilistic thing. Of course, this isn't instantaneous. And as what you'll find in your homework, turns out to be this proceeds over a very short amount of time and a short amount of redshift interval. It's like 150,000 years. 150,000 million years. 150. I have the number. What's the answer? Does anyone remember what the order of magnitude is? This? This is kiloyears. It's of order that. So this whole thing isn't happening instantaneously. It's happening over the course of a short amount of time in the history of the universe. But for our purposes, obviously, this is a very small amount of time. So what it looks like is that all of a sudden you have this photon which is no longer capable of interacting with ordinary matter, and so this photon just winds up propagating. And the way to think about it in this context of this propagation is that all of a sudden it's like, oh, now I can't talk to matter anymore. Photons and matter were very connected to each other. And the way in which, sort of, if you had a sort of overdensity of matter early in the universe, the photons would be highly coupled to that. Now, this is in all kinds of matter. This is only baryonic matter, not dark matter, as far as we know. But we think of this also as a decoupling, because it's when photons and ordinary matter stop really talking to each other. Another way to think of it is that you think of these photons now as scattering amongst all of these particles at high redshift, and then all of a sudden they stop scattering. So it's also called the surface of last scattering. So it's, in terms of what the ions are doing, this is recombination. In terms of what the photons are not doing, we call this the surface of last scattering. And in terms of the relationship between matter and photons, this is the moment of decoupling. All those three things are sort of the same concept wrapped into one. And why do we think of it as a surface? It's the same sort of thing as thinking of clouds as having a shape, right, as having a surface to them. Of course, those of you that have flown, I assume all of you have flown, you fly into this cloud and you're not like, oh, I'm about to hit a cloud. You sort of enter into it gently. You don't even notice where this thing begins and where it ends. I don't know, maybe some of you freaked out. Were you guys freaking out the first time you flew? This is, in terms that we can understand in 7b, you think of the surface as essentially an optical depth of 1, right? And at optical depths higher than 1, we can't see inside of it, so we think of this as the surface. Okay? So it's exactly the same concept as the surface, and because the amount of time that it takes to get to this point, and the amount of time it takes to get from us to being in a fully ionized state to a fully neutral state is so small, we think of this as basically just an instantaneously small, thin sheet. Okay. Any questions about the concept behind the surface of less scattering, about reionization? Okay, so let's look at the conditions for recombination. And as you know, this is a proton plus an electron changing to a neutral hydrogen atom, H0. Remember, we also, in the context of gas that we observed in the universe, call this H capital I, plus the ionization potential of hydrogen. Chi I is 13.6 electron volts, as you know, and we can associate that with a temperature, kT. K is 8.617 times 10 to the minus 5 electron volts per Kelvin. And so this means that the effective temperature we're talking about is something of order 157,000 Kelvin. So that's that magical temperature. So nominally what you'd expect is that if you look at the temperature of the microwave background today, and how does temperature go with redshift? Everyone agree with that? It was higher. And what's the way that we think about it in the context of, say, a black body spectrum or Wien's law? Why is this the case? Because what? Lambda? Oh, lambda. Yeah, sorry, I was thinking the other kind of lambda. Yeah, so lambda, how does lambda go? Lambda observed, lambda emitted, 1 plus z to the I was trying to see if somebody said -1 or not. So the observed wavelength increases relative to the emitted wavelength by this, and because lambda and temperature are related to each other, this has to be the case, right? Wait a second. Yeah. So there's a 1 over, it goes like -1. This is because this is temperature emitted, and this is T0. So if I put these both in context of T0, T0 observed is temperature emitted divided by 1 plus Z. I was being a little loosey-goosey with my E's and my O's.
Which is an E and which is an E?
This is an E. Temperature emitted is 1 plus Z times temperature observed. Okay? So nominally, you would just take the ratio of these two, and that would tell you the redshift at which this happened. However, you have to now think of this in the context of statistical mechanics, that you don't have to have every photon have exactly this energy. You can have a temperature of the universe and have some distribution of photons of different effective temperatures. And that is a way of giving you an almost completely neutral or almost completely ionized universe. So something that you'll need for your homework, and I won't go into great detail on, is the way in which we think about the equilibrium condition where we have some temperature and we have a set of particles, and the relationship between those particles and the number density of those particles is something that we can just write down in a statistical sense based on that temperature. This is something called the Saha equation. Sorry, yeah, I know. You're going to see this like 100 times in your career, so stop groaning. The number density of protons times the number density of electrons divided by the number density of neutral atoms is equal to 2 pi mass of the electron times the temperature divided by Planck's constant squared to the 3/2 power e to the minus chi h divided by kT. Charge neutrality helps us out a little bit. It says that the number density of protons is equal to the number density of electrons. And baryon conservation tells us that the number density of protons plus the number density of hydrogen atoms is equal to the total number density of all the hydrogen atoms and all the protons, right? So the total number density of neutral atoms and the total number density of ionized atoms. So NH is equal to N minus NE, because NP and NE are the same as each other. And if we write down something called F, which is the reionization fraction, this is Ne divided by N. So this is just the total number of ionized atoms, or in this case, because we're just talking about hydrogen, total numbers of ionized atoms divided by the total number of protons that we have around, whether they're ionized or whether they're not ionized. Okay, so this is how you should be thinking about reionization. And when we have this number approaching 1, we're fully reionized, right? Because this Ne will wind up approaching N. If we have no ionized electrons, that is, we're basically fully neutral, this number will go to 0. So F obviously goes, in the history of the universe, which direction? From what to what? From 1 to 0, exactly. So reionization is when F goes largely to 1, from 1 to 0. This is high Z, and this is low Z, and somewhere in between is what we call Z recombination. All right, so what you will wind up showing is that when F equals 0.5, so halfway in between, Z recombination is of order 1089. And this occurs when the temperature of the universe is about 2,970 degrees Kelvin. So basically, an order of magnitude smaller than this sort of nominal number you would come up with if you were just sort of taking the fact that the universe had to have that sort of, the temperature associated with the ionization of hydrogen. The time of recombination is 379 times 10 to the 3 years. So 379 kiloyears, or 0.3 megayears. What you'll find when you work this out, and I think we ask you to just do this on your homework in the context of matter-dominated universe, is the numbers will be slightly different than what we have here. And we also ask you to figure out why the numbers that you come up with are going to be slightly different. But they're going to be about the right size. Okay? So I won't go into the details of solving this, but I think I've given you enough now that you can essentially plug back in. And the way that you're going to wind up seeing is you're going to have some sort of functional form of F on the left-hand side and another functional form of F on the right-hand side. And you have to essentially plot F on the left-hand side and the right-hand side and see where the two of these things cross. So you have to actually solve this graphically. Okay? Any questions about that before I go into the history of the CMB and its use in the context of a cosmic ruler? You get sort of the physics now of what's happening as I go from a fully ionized state to a fully neutral state. Okay, so CMB, an actual prediction of the Big Bang. If you think about a universe that was always around, that is what used to be called the steady-state universe, which is the dominant idea of sort of cosmology, right? Even in the context of what Lemaitre had done and Einstein had done. Einstein introduced the cosmological constant because he didn't like the idea of a universe which was expanding or contracting. And without that cosmological constant, the universe had to be expanding or contracting. So he added this fudge term, which he wound up calling the biggest blunder of his life. Turned out to actually be right. So that's sort of irony. I don't know. Alanis Morissette completely destroyed my concept of what irony is through her terrible song. It's something. The point was that when Einstein postulated all this, Hubble's result from 1929 was not known. So it was not known that the universe was expanding. So even after that, people are trying to wiggle out of this universal expansion and talk about a universe that was basically always around. And maybe, and this is really strange, maybe the idea is that everything was always expanding away, but somehow as you expand away, you wind up sort of creating matter at a very slow rate, but enough so that if I come back a billion years from now, the universe also looks to be moving away from me. So the idea of sort of constant creation of matter was one of the things that people were holding on to in the 50s and 60s as part of the steady state. In 64, these folks, Wilson and Penzias, in Princeton, were making this big radio feed right here and trying to see what kind of long-distance communications they could do. And they did this at microwave energies or microwave wavelengths. And they would look off in a direction, and they would basically see on their detectors noise. And they figured that there was this extra noise in the system that they couldn't get rid of, and then they'd point somewhere else, and the noise wouldn't go somewhere. It was the same amount of noise during the night and during the day. And they finally realized that the problem was birds living inside of this radio horn and had left a lot of bird stuff inside. So they found a bunch of homing pigeons that were living inside of this thing, and they cleaned out all the bird stuff, and they got rid of the homing pigeons. I don't think they did like that, but they brought them to another state or something. It turns out the homing pigeons are really good at homing, and they came back. But in the time between them not getting their neck wrung and getting thrown out to the time that they came back, that noise persisted. And what they realized, because they wound up talking to some of the theorists nearby Princeton University, was that this may be the relics of the Big Bang. This background radiation was essentially just noise to them. And in fact, some large fraction, if you go back to your analog TVs and turn them on, a large fraction of that noise that you're seeing is actually relics of the Big Bang. It's actual noise that comes into your detector, your own detector. It was quickly realized that this was going to be a major triumph of the Big Bang prediction, which had been around for a while, but the steady state was winning. In the idea that if there was a beginning of time, then the universe was very hot at early times, and at some point, what we just talked about physically, going from a fully ionized state to a fully neutral state, must happen. And so you must leave over this relic radiation. In the 80s, a satellite was launched called COBE that measured very precisely the spectrum of this radiation. And what's remarkable is that to 1 part in 10 to the minus 5 or so, this is a perfect black body. In fact, it's the best black body that mankind has ever measured. What we can measure on Earth doesn't even come close. So something in space is basically a black body of temperature. It's radiating like it's got a temperature associated with this wavelength or this frequency. And when you look out in every single direction on the sky, when you're in space, or actually you can do this from the ground as well, the temperature is a black body, the 2-point-something Kelvin. Now it turns out that if you remove now this temperature on the sky, so you take off essentially the DC level and you see what's left, you see a little yin-yang on the sky. Because it looks like there's a colder spot here and a warmer spot over there. Now this is at 3 millikelvin, so this is down by a factor of 1,000 relative to this overall temperature. This is what's called the dipole moment, and it is due to the Earth's motion, or actually the sun's motion, or actually the galaxy's motion, or actually the local group's motion, through the Hubble flow. right? Remember when we talked about the Hubble flow, we talked about these sort of coordinates being fixed. Well, obviously, that's not exactly the case because we all have peculiar motions relative to all the things that we're orbiting around. And you can think of the galaxy as falling into Andromeda or Andromeda falling into the galaxy. We are falling towards the Hubble flow, towards Leo at 371 kilometers a second. Now, we know that the Earth moves around the Sun at 30 kilometers a second. The Sun is moving around the galaxy at 220 kilometers a second. So all that extra stuff is the galaxy itself moving through the Hubble flow. So there's kind of a preferred direction. This is what we weren't supposed to think about in the context of cosmology. There's indeed a preferred direction because we are moving in one direction relative to sort of the overall coordinate distance where we ought to be, right? Where's the center of mass of everything within our gravitational influence. So that's the origin of this dipole, right? And the Milky Way is here, so you actually start to see some of the effects of some of the Milky Way emitting sources in the microwave bands. But we go from there, one part in 10 to the 3 down to there. And then, as many of you know, we keep on going. And if we remove the dipole, what's left over is a lot of stuff from the Milky Way. Remember, this is how we view, in this case, we're viewing the sky in galactic coordinates. The galactic center is here, the Milky Way is here, the north galactic pole is here, the south galactic pole is here. And you see what the typical fluctuations are, delta T, of 18 microkelvin. So we're down by another factor of, say, 100 or so from here. It's this stuff here that are the ripples of the cosmic background radiation. The background is almost exactly uniform, but it's not perfectly uniform, and that's a good thing. If the universe was perfectly uniform in 1 part in 10 to the 10 or 1 part in 10 to the 12 at the time of recombination, then there wouldn't be enough time in the history of the universe to get you guys around, because you need to take this stuff, which is temperature anisotropies, and as we'll see on the last lecture on Thursday, these temperature anisotropies can be directly translated into density and homogeneities. And density and homogeneities are the things that make structure, right? If the universe was perfectly uniform, then there'd be no special place in the universe where matter would love to congregate. So you need to have these inhomogeneities for us to be able to have structure in the universe. So this is the seeds of structure, right? In many ways, this is the seeds of galaxies. This is the seeds of you. Now, this is now not causally disconnected from you because you're receiving this light. So in principle, this exact light that hit in 1980 was affecting you, or 1990 or whatever, was affecting you way back when. Yeah, wait. Who was born after 1990? Oh my God. All right, anyway. So maybe these actually affected your birth, right? These actual photons affected your birth. So this is not actually the seed of the Milky Way. This is the seed of something at redshift 1100, which will wind up making essentially large clusters later on in time, right? And somebody who's now part of this large cluster, who's observing light from our direction, is observing the seeds that wind up making us, right? As many of you know, Professor Smoot in the physics department won a Nobel Prize for the detection of these ripples in the cosmic background radiation. And since then, people have launched satellites to get better measurements of the distribution of these clumps, because this is what's going to turn out to be our standard ruler. Here is a picture from the Wilkinson microwave anisotropy probe, and it's a nice paper, 2003. It's often referred to as WMAP. And this is the satellite that has been producing all of the results, or largely all of the precision results that we've been referring back to in our book, right? So we keep saying the WMAP cosmology. That's the 2003 best bet for what H0 is, for what omega matter is, omega lambda, et cetera. And it comes from this map. Planck is going to be launched. Just one sec. Planck has been launched and is going to start putting out maps that are even higher precision. That's sort of a simulation of what they're expected to see. And by the way, they were able to get rid of the Milky Way foregrounds by looking at the spectrum at essentially every pixel and saying that the cosmic background radiation is going to have a very certain spectrum associated with it. And everything that doesn't have that spectrum, they remove that off. So that's how we can essentially see through the Milky Way now. And you can see that some of the structures from, actually it's easier to see in the picture before, some of the structures like these cold spots up here wind up persisting up here. It's a little hard to see, but you can still see some of that. And then as we get to some very cold spots over here, right, and some hot spots as well, we can see that persisting through Planck. And then what Planck is expected to see, this is some zoom in, and you see the units here of minus 300 microkelvin to plus 300 microkelvin. They're expected to see very, very high resolution structure of the cosmic background radiation, getting at some of these detailed ripples. Okay, so there were a couple of questions. Yes?
Yeah, my question was, what's a negative Kelvin?
Negative Kelvin relative to the average background radiation of 2.725.
Okay.
So it's slightly less than that. And then there's some that are slightly hotter. Yeah.
So do the hotter regions correspond to less dense regions? Because you said that the radiation gets through because there's no matter for it to interact with. So, right?
No, they're related to each other in a linear way. They're not inversely related. So the way to think about this is what happens right after all of the ionization business, and now we've gotten into neutral territory, right? So the universe was slightly more dense right here, and likewise it was slightly hotter. We'll do the mathematics of that on Thursday, but yeah, it was slightly hotter here. So actually, if you're thinking about it now, if you really want to think about this not in terms of a surface of less scattering, but at what redshift did this happen, there was a decoupling slightly earlier in the history of the universe here, or sorry, slightly later, because it took a while for that local part of the universe to expand just enough to get more neutral. So this is a nice sort of representation, now not of in 2 dimensions where we spread out the celestial sphere, but now sort of if you were standing in the middle and looking out, you would see the cosmic background radiation around you. And this is from WMAP, and this is basically real data. So this is the seeds and the ripples of structure. All right, so any questions about that? I'll go into now some of the physics of these ripples, and then we'll see how this relates to standard rulers and cosmology. Yes?
So I'm just trying to get like sort of a feel for sizes. Like, would each little dot be like a huge galaxy structure, or would it be like a galaxy?
No, these would be like superclusters. We'll figure out, by the way, the typical distances between hot spots and cold spots is about 1 degree. And we'll see what number that translates into in terms of physical scale. Right? Okay, so let's do the origin of the ripples. I'll just get rid of it. The way to think about this is as perturbations. So we have some probability of some size scale of a perturbation as a function of size of the perturbation. We'll talk about, not in great detail, but on Thursday we'll talk about these perturbations both in the context of essentially density enhancements and temperature enhancements. But what you should recognize is that in the very, very early universe, it's not perfectly uniform. So there are some places where you're slightly overdense and some places where you're slightly underdense, and likewise some places where you're slightly hotter and some places where you're slightly colder. And there are many perturbations which are very small, and fewer perturbations which are very large. These perturbations in the early universe travel around. Now in the context of an expanding universe, so it's a little strange to think about. And this is one way to think about this is as cosmic sound. So I have this slight overdensity, and it just, let's say I have a slight overdensity, 10,000 years after the Big Bang in this little spot right here. That overdensity, the knowledge of that overdensity is going to travel out. And it actually travels out like sound does. These are longitudinal waves that propagate through this ionized plasma. And because we think of this in terms of sound, and this is relativistic material, it turns out that the sound speed is the speed of light divided by square root of 3. Has to do with the relationship of pressure and density and temperature. But in relativistic plasmas, that's the sound speed. So again, think about this now in terms of ripples in a pond. Around the time of the Big Bang, I throw in a pebble, and there are some ripples that propagate outward. They propagate out in a spatial sense through an expanding universe now at the rate of c divided by square root of 3. So very close to the speed of light, these ripples are all happening. Now, think about this distribution here. Think about ripples that have sort of different amplitudes, or they're confined to a smaller place when they first start off on this pond. Think about essentially rain coming down on this pond. Rain starts at t equals 0. You've got all these perturbations, and you've got all these ripples which are propagating outward. And if I just stop and I look at this movie, right, sort of at t of time of recombination, I look at this pond, I'm going to see not a uniform sort of scruff of waves that are up and down, right? I'm going to wind up seeing essentially the imprint of the time it's taken from t equals 0 to the time of recombination, because every single wave will have only had a certain amount of time to propagate outward before I stop the clock. And why am I saying stop the clock in the context of the CMB? It's because that's the moment when matter and radiation decouple from each other. So the imprint of those perturbations as they had traveled out from the time of the beginning of the universe is still there in the cosmic background radiation. I hope this becomes a little bit more clear as I talk about this and start putting some numbers to it. But that's sort of the hand-wavy statement of how we wind up getting those ripples. The largest distance that these sound waves can travel until T recombination is something that we'll call d sound. And this depends upon sort of the overall size scale of the horizon of any particle at any one time, divided by this sound speed. So this is really some sort of T recombination times CS. If we want to frame it in the context of a horizon scale, which I'll go through the mathematics of in a second, this is the horizon at time T recombination divided by square root of 3. Okay, so let's talk about the meaning of horizon scale. It's related to proper length. I can find my notes. Okay, and the horizon scale doesn't just have meaning in the context of the early universe. The horizon scale has also meaning today. How do we think about a horizon when you're sort of in the middle of the ocean and you're freaking out because you don't have your radio. It's the farthest distance that you can see, right? And the Earth is curved. I'm sorry to burst some of your bubbles. And so, if we have a source which is several kilometers away, we're very likely going to see it. If it's thousands of kilometers away, we're not going to see it. The horizon is how much you can see around you. And the way to think about a horizon in the context of cosmology is it's really your sphere of influence. Everything within your horizon, because by definition you can see something right at the edge of your horizon, everything inside of that is causally connected to you. So it was related to all the things that happened that led up to you and your birth and right now and your measurements. Right? So something which is really close by, only a gigaparsec away, I can see that galaxy. So clearly light from that galaxy influenced my ancestors, right? If I go farther and farther away, I'm starting to get to the moment or the distance where light is now just arriving from there. And this is because of the finite travel time of light and the finite history of the universe. Yes? Your question? No. You're okay with that? All right. So particle horizon. It's basically the proper distance to a very large redshift, approaching infinity. Another way to think about this is it's the distance to photons emitted at time t equals 0. In a matter-dominated universe, recall that you showed during the lecture that Yuk-Yun touched on was R goes like 6 pi times g rho 0 to the 1/3 t to the 2/3. So if we think of the d horizon going through the same mathematics that we did last lecture of r of t going from 0 to time t, say recombination, c dt r of t. We won't do it, we'll just do it at any time t, right? So this is generically true. If I now want to do this in a matter-dominated universe, I can say that r goes like t to the 2/3, or c prime t to the 2/3, some constant out in front. So d horizon is c prime t to the 2/3 times c 0 to t of dt c prime t to the 2/3 on the bottom. And if we just do this integral out, I'm just breezing through this because it's just the algebra of it. 3 times t to the 2/3 c t to the 1/3. So the horizon goes like 3tc in a matter-dominated universe. Remember, in a radiation-dominated universe, we said that r goes like t to the 1/2 power. So instead of a 2/3, we do the same thing out with a 1/2, and we get this goes like 2 times tc in a radiation-dominated universe. Now, you have to bear with me for a second. I have to fudge something, okay? But it's all on the up and up. In the very early universe, what dominates, radiation or matter? Radiation. A little bit later on, matter starts dominating. Why am I not doing this in the context of a lambda universe? Because we're talking about stuff that's happening really early on in time. Typically, when people are doing this sound time or the sound distance in the context of the CMB, you think about this in the context of the recombination time. So this is looking out at the time of recombination. I'm a particle, and I just became neutral. Then I look out and I say, how far away can I see? Right? And intuitively, you know that that's not nearly as far as we can see today because the universe wasn't that old. And light hasn't had enough time from very far away to travel and influence the particle that's observing the universe right then. Okay? We usually do this horizon distance in a matter-dominated universe. So 3ct recombination divided by square root of 3. This is square root of 3ct recombination. Why is that okay? It's not really a fudge. This is okay. Why do you think it's okay? You remember what redshift? There was a transition between matter and relativistic particles in terms of which of those two factors contributed equally to the Friedmann equation? Yeah, it was like at 3,000. So from redshift of infinity to 3,000, or thereabouts, radiation was dominating. From redshift of 3,000 to time of recombination around 1,100, matter was dominating. So you actually have to use a full equation for for getting d sound. You have to use the full equation for the horizon, and there you can't just trivially plug in r of t goes like t to the 2/3. You actually have to plug in the full solution of how r of t goes, now using both radiation and matter. So anyway, what we're doing in a hand-wavy sense is saying, well, from 3,000 to 1,100, that's actually a long history in the age of the universe. Actually, it turns out to be a long age in the universe relative to the time it goes from redshift of infinity up to 3,000, or down to 3,000. Okay? So most of the universe at the time of recombination, most of the time of the universe had actually been dominated by matter. Okay? So I'm okay with this, if you're okay with this. It's about that. All right. So all of this, just to say that we can plug in the time of recombination and get a horizon size. And we can then plug in the horizon size to get a sound size. T recombination, what did I say, 379 kiloyears. And if you plug this in, you get that d sound is equal to 5.4 times 10 to the 21 meters. And this is about 0.2 megaparsecs. All right, so let's think about this for a second. What does this mean? This means that at the time of recombination, a particle which just became neutral is looking out around it, and it's looking at a horizon which is large, but smaller than that horizon by a factor of square root of 3 are all the particles around it and all the perturbations that could have influenced its own temperature. Okay? So let me say that again. You have perturbations in the very early universe. Those perturbations propagate out freely at the sound speed of this plasma, which is the speed of light divided by square root of 3. And you sort of stop the clock at T recombination, and you look how far those perturbations could have traveled. It means that when I observe, something which is right here, and I observe something which is right here, if I'm within this D sound physically, then these two guys were talking to each other. If I now observe something which is farther away, it turns out that these two guys are not talking to each other that are farther away because they're outside of their own, not only their own horizon distance, but more importantly, they're outside of this D sound distance. Okay? Everything within D sound, you get to talk to. Everything out of D sound, you don't get to talk to. Those perturbations don't get to propagate. D sound is a very important distance because this acts as a standard ruler. it says that if I look out at perturbations on the sky and the cosmic background radiation, I should see essentially correlations of hot spots and cold spots. And indeed, when you analyze that cosmic background picture that I showed you from WMAP, right here, what your eye might be able to see is that, every time you find a cold spot, you sort of have to go a certain distance to get to the next cold spot. Or likewise, if you find a hot spot, you got to go some other distance to get to the next hot spot. That distance corresponds to d sound. So now I have an angular size scale on the sky. And this is what you usually see as what's called the power spectrum of the cosmic background radiation. And you can more or less just take the whole sphere and move it around by a certain amount of angle. And you can move it around, and you find that if you move it by about 1 degree, and you multiply those two together, you wind up finding a huge amount of power. So that means that if I have a hot spot here, I move 1 degree away, and I have another hot spot, preferentially. Likewise, if I have a cold spot here, and I move 1 degree away, I have a cold spot, preferentially. Right? It's not exact, but you can analyze the power spectrum to do that. So you get a huge amount of power at this angular scale, about 1 degree. And that 1 degree scale corresponds to this sound distance. So if we think about this angular scale of about 1 degree, or in this case theta, we do it in radians, this is going to be d sound divided by dA to time of recombination, or the redshift of recombination. And that angular scale in degrees is 1.03 degrees. And that means that dA to the redshift of recombination is about 11.7 megaparsecs. So something which is at a redshift of 1100 that had the age of the universe until that time to propagate outward has a physical scale of 0.2 megaparsecs, so 20% the sort of size scale of the local group of galaxies around us today. And because the angular scale is very large and corresponds to about 1 degree, this means that the angular diameter distance to that source, or the surface of last scattering, is 11.7 megaparsecs. These are pretty small numbers on cosmological scales, right? That's a small number. That's a really small number, given that we're talking about a redshift of 1100. But now you know that we can make a measurement of distance very precisely to the surface of last scattering. We're not doing it in luminosity distance. Luminosity distance would be vastly larger. The luminosity distance to the surface of last scattering is going to be 11 times 7 0.7 megaparsecs, 1 plus z squared. So this is about 10 to the 6 times 11.7 megaparsecs. It's a very large number, right? Now here's what's interesting. Angular diameter distance is related to luminosity distance, which is related to the proper distance. Proper distance is essentially just the integral of the Hubble constant as a function of redshift, which itself just depends upon fundamental parameters of the universe that we can measure today. By making a measurement of this angle, and by the way, you can also see what are called harmonics of this, because this is waves sloshing around in this relativistic plasma. And so you wind up getting on smaller scales, by a factor of 2, by a factor of 4, this sloshing. And this sloshing is damped for reasons I won't go into, but these all wind up being related to this hump right here. The amount of damping that you get turns out to depend on some of the other cosmological parameters. And it allows us to actually crank up and down different cosmological parameters. This is all the mess of data that came out before WMAP. And we can change parameters like Hubble constant, and we can change the total value, in this case omega k, or just omega total, from 0 up to 1. Actually, they're going -1. And you see how this power spectrum winds up changing. So you can just play around with this and crank up and down. These are many, many parameters that I haven't told you go into the Friedmann equation, but they do. Well, you'll do this when you get into grad school. But you can crank up and down all these numbers, and you can wind up fitting for the best cosmology. And in fact, if you think about this not so much in terms of the value of omega 0, you think about this in terms of whether it's flat, open, or closed. Omega total of 1.0 is flat, and open and closed are going to have different values of omega. You can look at some of the early data that showed high resolution images of the cosmic background radiation over 25 square degrees, and you can see that in an open universe, you wind up having smaller patches, and those patches are closer together of hotspots. In a closed universe, they appear to be farther away. And in sort of the Goldilocks universe of being just right, they're about 1 degree away from each other. So indeed, this is what we observe. This allows us to look at the distribution of matter and neutrinos and photons, dark matter, at the time of recombination and compare that to what's driving the Friedmann equation today. And what you see is the distribution of what's driving the Friedmann equation today. Dark energy is dominating. Dark matter is a large part of that. And the atoms, the ordinary baryons, is only 4% of what dominates the expansion of the universe today. And at the time of recombination, it was quite different. Dark matter was dominating over photons and dominating over neutrinos. And atoms contributed more, obviously, than dark energy. Dark energy is not even on this pie graph. But you see that our assumption of using R going like t to the 2/3 to figure out this horizon scale was actually appropriate. All right, so I'll end with that. I have office hours today from 3:30 to 4:30, and we'll pick up on Thursday in the last class with just a brief mention about the Sunyaev-Zildovich effect, brief mention of baryon oscillations, and then we'll kind of do all the Big Bang until the time of recombination.